I'm currently working on trying to resolve an issue with the bootloading from a floppy disk for my PDP11-34. And if you've been watching this series of videos, you know I've had a lot of issues with this machine, many faults I've been working my way through, and got the basic PDP pretty much running. In the previous video I fitted a replacement memory card. That wasn't the problem, I don't think, but to help me fault find I wanted a more standard memory card, so I've fitted one that there is technical documentation for, so it will make this next part of the process easier. The issue I'm looking into at the moment is I'm trying to boot from floppy disk, but it's while I could originally read the floppy disks using PDP11 GUI, I can't now read them, and what happens is the machine will hang in a bus cycle if I try to run anything that's approaching a proper read of the floppy disk. And had a quick look at this off camera, and I did find a fault with the RX 211 interface card. There was a multiplex that wasn't working. It was causing the machine to hang randomly, so I replaced that. It wasn't part of this problem, but I replaced that just because it was causing another issue. Problem when you get a fault like this is it's where to start looking, because it could be a fault with the main PDP CPU, it could be a fault with the interface, it could be backplane memory, it could be the control card on the floppy disk, the drives themselves, the interface electronics. And so it all gets a bit complex, and on top of that you of course have configuration. Just one quick note, I mentioned previously that I was having a problem with the bootloader on the I've got a bootloader card in this, an M9312, and there had some faults with that was causing some issues. And one thing that can be a bit confusing if you're just starting to repair these machines and you've got a bootloader is if we look at the bootload code for the bootload PROM, so this is the one that's supposed to bootload the floppy disk that I have here. They always have a header at the beginning. These are small PROMs that you plug into the bootloader card. So you have a header here, and as with most booting on a PDP, you have two addresses, 24 and 26, and they contain the address. 24 contains the new program counter value, and 26 contains the new status word, the program status word that will be loaded into the CPU, and obviously that causes it to branch to the new address, and in theory this address should be the start of this code. But there are other ways of getting into the code, so it's fairly flexible. So what can be a bit confusing is this particular PROM is mapped to an address, a virtual address of 173,000. And that means that this value is mapped to a virtual address of 173,024. And so if you read that address, the obviously physical address is 773024. So if we read that, so we'll put in 773024. You can't really see what's going on here, but if I now try and load that address and examine, I'm getting a value returned of 165020. So it looks like the PROM is wrong, but it's not. The PROM value is correct. What happens here is the bootloader card remaps the addresses within that memory range, and it looks something like this. So you have the start of the this is the monitor program in effect and diagnostics. That ROM is pretty much always there, and then you have the optional ROMs to use to bootload your specific hardware. And you start with the first bootloader. You can put up to 2 images in each PROM, but effectively they kind of daisy chain their addresses, and you just as you add them, then the address moves down, and each one's identified by a 2-character code that you can trigger from the remote terminal. But I have the switches set to this address, so it boots straight into the monitor, If I try setting this address, or if I try branching to that address, then the machine hangs, and that's what the problem is. If I try to boot from floppy disk, it gets part way into the process and then the PDP locks up. So the question is where to start looking when you have an issue like this. So before we go any further, I'll just move the camera so you can see the control card on the floppy disk. So looking at the floppy drive, you can see there's a large CPU control card. I've got it hinged up at the moment, as you can see, and then underneath that is the interface card that sits between the CPU control card and the actual drives, and then you have the actual drives, of course. So in terms of the system, you have the PDP CPU, its backplane, the RX211 interface, the memory card. The RX211 talks to this CPU card. You can see the large ribbon cable coming in, and then that interfaces with the interface electronics on the RX02, and then you have the actual drives themselves. And of course the fault could be anywhere in this chain. So and of course it could be a fault with the floppy disks themselves. So it's a question of where to start when you get a problem like this. So I'll just move the camera back. So the problem we have is, as I said, where to start looking when we get a fault like this. And I tend to, you can either work from the floppy drive back or from the PDP forward. And I tend to go from the PDP because we've already worked on this and we're reasonably confident at least some of it's working, but we don't know what the state of the floppy drive controller is. So if we can get the machine itself to give us a bit of information as to what might be going on, then it would be helpful. It might make our life easier. Now luckily there's a lot of documentation available for the PDP11, and part of that is the documentation for driving the RX02. It's quite complex, it gets quite involved, but if we break it down into sections it becomes much easier to deal with. So the first thing to bear in mind, and I don't really like working on these RX211 boards, they're very tricky to work on. Now they're actually a state machine, and it's all hard coded, so it's very difficult to fault find on, because what you're looking at any instant depends on the sequence of events prior to that. So when you do a full reset, the RX211 should be in its default state, and you then supply it with commands and data, and it will step through the state machine to provide the various functions that are required for the interface. But at each step it requires specific information. You access the RX211 through two addresses. So this one's currently mapped to 777.170 and 777.172. The first of those addresses is the control and status register. Now it says it's a control and status register, but they're not really registers. They're a collection of circuits that are accessed through that address. Which particular circuits you access at any one time depend on the current state of the state machine. The second of the two addresses is the data transfer port, and again it will vary in its function depending on the current state of the state machine. It might be used for sending data to the RX02, or it might be used for getting data from the RX02, and the software that drives it has to keep track of the state machine and make sure it's driven properly. And in theory it's meant to guarantee that you don't corrupt the data on your floppy disk. So when you come to testing this, it's always best to use a scratch disk. You don't need a boot disk straight away, and I have a scratch disk in the floppy drive, so I know I'm going to corrupt the data on it as I go through the testing, so I don't want to risk a proper boot disk or a proper software disk. You could try write protecting the disks, but that's not really that successful, because whether the write protect works or not depends on how well the system's working. It might just decide to ignore the write protect and go ahead and write the disk anyway. So the way that the interface operates is that you set a function, you do a reset, set a function in the control register, and the functions are listed down here as to what particular functions are available. So you just set the bit codes. So 000 for example is the fill buffer, so you put that into these 3 bits, set the go bit to a 1, send that to the RX211 card, and you will have started the fill buffer function. But there are several steps in each of these functions, and as you work through the functions you have to send specific data to the second register. And the problem I'm getting at the moment is when it moves from the initial sending of the function, I immediately get a fault, an error, and there's an error line comes back from the RX02, and that's being set as soon as the RX02 is sent any data. This is control data, not necessarily data to write to the disk. So there's obviously something wrong, probably with the drive CPU controller card, but I need to try and narrow this down and make sure it's not a simple fault with the RX211 or something else. I just need to try and narrow this down a bit. So what I do in this instance, because I can't run any detailed software because it hangs the machine, what you can do is drive the floppy disk drive manually. And you can manually go through these functions, and that's what we're going to do. I'll do the first one here. In fact, we'll do a right sector because that's a bit easy to see if it's working on the floppy drive, because we'll see the head move if it's working. And what we're trying to do here is establish how much of the system, if any, is actually functional. So is it responding to commands? Is the interface doing anything at all? And will it accept commands, that sort of thing. So the first thing I generally do is send a reset command. So if we look at this bit 14, you'll see that it says RX init, and that it's a bit like the reset you get on the backplane, except it doesn't reset everything else, it only resets the drive. Resetting the entire system doesn't tell us much because it's there's kind of a hard-coded reset attached to the AC low input, and it doesn't really tell us anything because it's a hard-coded function. What we want to do here is see if the system is capable of accepting commands through the interface card, and whether it can successfully send those commands through to the drive, and if the drive will respond. So we'll start by setting just that 1 bit, and we'll send that to the drive through the interface, and we'll see if the drive actually resets. So we need to select the correct address. As I said, that's 777170, and we'll set just that 1 bit, which is a value of 40,000 octal. Send this, and if this works, then the drive should reset. Okay, well, hopefully you heard that the drive did in fact reset. We'll try doing that again. Okay, so that tells us quite a lot. There's quite a lot of the system needs to be functional for that to work. Obviously the PDP has to be running so it can send data out. It needs to be able to send the value successfully to the RX211. It doesn't tell us if all the bits are working, it only tells us that particular bit is working. The RX211 can then send the data through to the control CPU card in the drive. The control CPU card can successfully control the interface card and set the drive solenoid relay and drive the stepper. You can't see it, but I could see the drive stepper actually moving. It drives 1 track away, then back to the home position when you reset, and that is moving. I'll move the camera later on so you can see this moving. So we know quite a lot of this is working. What I'm going to do now is make sure that the RX211 can successfully accept the function values we're sending to it. So I'll move the camera and we'll just send various functions to the board and make sure that the latch that accepts this is actually working. I won't go through the entire schematic, at least not in this video. If you're interested, let me know and I'll go through the RX211 card in more detail once it's up and running. But we're looking initially at this latch here, and it's E37, so that's this device. And what we're looking for is that when we send the command, it comes into the input on these 3 pins, and it should set the function output pins. So we've got funct 0, 1 and 2, and all we're doing here is latching those 3 bits that we set in the command into this latch. So that's the first thing, because that governs the overall operation of the interface. Okay, so the pins we're interested in are pins 10, 12 and 15, and they should change in response to me sending commands through to the board. So we'll just reset again just to make sure they're all clear, and then we'll check that they're all clear. So pins 10, 10 there, 12 and 15 should all be low, which they are, so that's working so far. And what I can do now is send a command, a function command that should set the bits. So I'll send a value of 3, that will set the first bit to a 1. So I've sent a value of 3, and we should now find that the first bit has changed to a 1, and it has, you can see on the scope there, yellow trace. The other 2 bits should still be 0, which they are. So we'll try another value. I'll reset it first because we've now started a function, so I need to reset that. So I'll do a reset, and now I will send, in this case I'm going to send a value of 5, and that will set the second bit high and the other 2 still low. So I've sent a value of 5. So the first one should be low, the next one should be high, and the last one should be low. Okay, so I'll go through the other combinations, and then if they're okay, we'll come back and continue. Okay, well they all worked, so at least it's able to accept commands, and now we know that it's latching the correct commands. We can start looking at the overall behaviour of the system. There's no point doing in-depth testing till we know that the board is actually capable of receiving the correct commands. So I'll move the camera down so you can see the display on the console. So looking at the console, I'm just going to turn one of the lab lights off and see if I can cut down on any flicker that's on the camera. Hopefully that makes it a bit clearer. So what we're going to do is try sending some manual commands through to the drive, and as we work our way through the various commands, it should help us determine if and where the faults lie. So first thing is make sure we got the address of the first register, so 777170 is correct, and we'll send a reset command, so we set the reset bit. Okay, and if we read back the same address, notice the values change. So as I said, the state machine will tend to present different registers depending on where you are in the state machine. So although there are only 2 addresses, there's a number of different registers that we access as we go through the read-write process, and you need to keep track of where you are as you apply the various functions. Okay, so we've reset the drive, and what we're going to do here is we'll do a write sector function. So that's a value of 5. So if we look at the document here, then the function we're interested in is the write sector, which is a function value of 0, 1, 0. And if we look at the way that we have to format the instruction, it's these 3 bits. So it'll be 0, 1, 0, and we also have to set the go bit, so it'll be 0, 1, 0, 1, which is a value of 5 in octal. So if we set a value of 5, make sure we've got the right address, 5, we write that, and what we can now do is re-examine the same register. And notice now that we've got a different value, but the important thing here is the 2, we've got 204. So if we look at the format of the register, that bit indicates that the TR bit is set to a 1, and the TR bit basically means that the interface is ready to send or receive data. So in this case it's waiting now for the first value for us to send, and the value it's waiting for is the sector address that we want to write to. But it's the next register, the 777172 register, that we need to write that value to. So if we move on to the next register, this is the correct register we want to send to, and in this case we'll send a value of 100 octal. It's our sector address, so we'll deposit that. The address that we send the next value to is the same, so in this case the next value we send is the track address, and I'll use track 60, just making up values here. As long as it's within the acceptable range it should work. And I don't know if you heard that, but the drive actually moved. I'll show you, I'll put the camera over there later on and show you it actually moving. But we know that the drive accepted all three of these command steps. It's driven through to the, have a quick look, it's driven through to what looks like the correct location. If we now go back to the first address, 777170, and we examine this, now if we look, this number starts with a 1, and if we look back at the register, this is the error bit. So as I said, it comes back with an error each time we send any data to it, which is why the higher level software is failing. It's just getting an error from the drive. One other thing we can do as part of this testing to try and pin down where the error might be coming from, it's obviously coming from the drive, but what's causing it? If we reset the drive, so again I heard the stepper wind back to the home position. Okay, what we can do now is restart the same function, so we'll restart the right sector function, so we send a value of 5, examine the register, notice we've got a value of 2, that's the TR bit set. Go to the next register at 172, we'll send a value of 100, deposit that, and we'll now go back to the first register again and examine this, and again the TR bit is set, which is good. It means it's accepted the command. Go and enter a value of 60 in the second register, and again I heard the drive move, so it's accepted this without problem. And so what we can do now is go back, examine this, but again we've got an error. So I'm going to try something else. We'll try a lower value, examine it. Notice this time there's no error. So what I'll be doing, I'll do it off camera now. I'm going to start working my way through various values, doing this same thing, driving to different offsets, tracks, sectors, and see where the problem comes in, and if it's at a boundary, so if it's a particular bit being turned on or expected to turn on and it's not, I can then start trying to track that down in the drive control electronics. So before I finish this video, I'll just move the camera and let you see the drive actually moving. I don't know if you'll be able to see this or not. You can kind of see the lead screw buried right down in there, and you'll see the carriage moving as I send this command. So I'll do a reset first, and you should see it do a reset in response to this. It's fairly quick, but you saw it move off the home position and then back onto it. And I'll now send the command to try and write a sector, so you should see that the lead screw will drive the head off the home position by quite some distance. And as you saw, hopefully it's moved. We'll do a reset and it drives back. Okay, I'll just move the camera back. So as you can see, quite a lot of the interface is working. We can successfully carry out some commands. I don't know if all the commands work, but what I can do is work my way through them, try each command in turn, try various values, and then we'll see where it fails, and by the time we've done all this we should have a good idea as to what particular function is failing. Once we know which function is not working, we can then start looking into the control electronics in more detail. So rather than just looking at everything, we can focus in on the bit that's responsible for that particular function. And as I say, by the time we get through all the various functions and commands, we should have a good idea as to where the problem lies and how to go about fixing it. So this is the approach I take. It sounds very long-winded and time-consuming. It does take a while. It takes several hours to work through all the commands, but it's far quicker than trying to just sort of thrash around and figure out what's going on with a logic analyzer. If you have another unit to compare, then obviously you can swap the various bits out. I don't have another RX02, so I don't have a spare controller board for it, and I don't have a spare RX211 either, so I've got to try and repair what I have, and I've got nothing to compare it against, so I've got to go through using schematics and the technical documentation. Makes it interesting. It's quite a challenge to fix faults like this because, as I say, the fault could be pretty much anywhere. But using this method, at least I can hopefully narrow it down.